So today we continue the previous discussion. Okay, so chapter atom class 12, and here we discuss chapter atom. Okay, so previous class end here. Okay, we calculate the force of attraction between alpha particle and gold foil. Okay, so here we study that alpha particle trajectory. Okay, so that's the alpha particle path, and here we study the trajectory of path. Okay, we study alpha particle trajectory. Okay, suppose this is a gold foil. Suppose this is a gold foil. Okay, this is called gold foil, and here that's some alpha particle source here. Okay, this particle is look like this, the state path, and one particle, alpha particle, back in that direction. Okay, and top of that here slightly deflect. Okay, actually in that direction, and on top of that I deflect in that direction, and this is top of that deflect in that direction, deflected in that direction, and here the state. Okay, okay, so here we introduce another parameter. Suppose this is the b, this length is called b, and this is called impact parameter. Impact parameter. Okay, and here is the source, alpha particle source here, and that direction. Okay, and this is a gold foil. So if the alpha particle move and in that direction, okay, at the center of the gold foil, you see that alpha particle deflects same path. Okay, there's a 180-degree difference. Okay, so scattering angle of this alpha particle, that is a 180-degree, means a pi deflection here. Okay, so alpha particle here distributed with the impact parameter b. Okay, and beam of scatter of various angles. So one angle more pi, one particle, and before top of that is scattered, but obviously the more this path in that direction, obviously more, but lesser than pi. And here this particle, you see that there is a minimum or less than 180 degree, 1 degree deflection. This particle and this particle less than 1 degree deflection here. Okay, so here main important concern, the impact parameter b is small. Okay, if this b is small and where the scatter in the one particle by pi. Okay, you see that there's a one particle, these particles scattered by pi, 180 degree deflection, because alpha particle be the plus, and here some particle are present here inside that gold foil, that particle be the plus, and plus or plus, so like charges, so there is a deflection here. Okay, so this experiment determine the upper limit of the nucleus. Okay, and you here see that this actual alpha particle trajectory experiment define upper limit of nucleus. Okay, so why upper limit? Because if I say that's the nucleus, there's a positive particle here, and you see that, and there's a alpha particle here, that is a nucleus, there's an alpha particle, and you see that there is a deflection. Okay, and here in top of that, okay, there is a deflection here, and here the deflection is less. So if we find that at that point, okay, at that point here, we get almost 90-degree deflection here, but top of that here deflection is less than 90 degree. So I think we say that that is the upper part of the nucleus, and similarly that this is the bottom part of the nucleus. So that's why this experiment, okay, our observation has defined that upper limit of nucleus. That's why this called. Okay, so there is a nucleus, and surrounded by the electron, and if electron is rotating in this orbit, okay, other orbit, like a planetary model. So here we study electron orbit, and if electron is negative particle, okay, this electron also be that negative, alpha be the positive, obviously deflection in that direction, okay, positive or negative, so that's why we are the unlike charges, so there is some attraction here. Okay, now study the electron orbit. So an important concept is electron orbit. Okay, so electron actually rotate in that orbit. Okay, this orbit is actually the circular path or circle is orbit. Okay, now I choose suppose I choose a orbit here. Okay, and here is that electron. Okay, and if the electron is rotate, okay, suppose is electron rotate in that direction. Okay, so there is some force here, the tangential force. Okay, and if the electrons rotate, so there is a towards center seeking force obviously present here. If the electron is negative particle and charge is negative, so nucleus is positive, so there is some attractive force here. Okay, and this attractive force is called a centripetal force. This is called centripetal force. Okay, and this centripetal force, if I say that is F C, suppose centripetal force, that is equal to mv square by r, and there's a radius and there's a velocity, tangential velocity, mv square by r. There's a tangent represent velocity, you know that from classical mechanics class 11. Okay, so now if the charged particle, so there is a electrostatic force. If that is to this to a charged particle, if I treat it as a charged particle, we get a Coulombic force. So that is equal to Fe 1 over 4 pi epsilon naught. So suppose we say that is equal to this particle charge is E, and this particle also charge say that E. Obviously consider the magnitude, E times E by separation is R square. So 1 over 4 pi epsilon naught E square by R square, that's the electrostatic force. And these two forces be equal. Okay, these force and this force will equal. So that is equal to Fe. So you get finally mv square by r, that is equal to 1 over 4 pi epsilon naught E square by R square. Okay, so finally we get radius of the orbit. Finally get r. So these are with the cancel. Finally the radius of the orbit is r equal to 1 over 4 pi epsilon naught mv square, and top of that is E square. That's the radius of the orbit. That's very important derivation. Okay, so if electron velocity here in that direction or opposite direction maybe, so obviously there is a velocity. So if the velocity is here, motion, electron are in motion, so there is a kinetic energy. So that kinetic energy means that half mv square, that is half m, and the v we get from v here, v square we get E square by 4 pi epsilon naught m r square. Okay, so that is equal to E square by 4 pi epsilon naught m r square, m be the cancel here. So the kinetic energy get half E square, and so 4 to the 8 here, 8 pi epsilon naught r square. So finally kinetic energy get, that is K equal to E square by 8 pi epsilon naught r square. That's a kinetic energy of that electron. Okay, so if the kinetic energy, obviously there is a electrostatic potential energy. Why that's called electrostatic? These are called two charged particles. So if kinetic energy, so there is potential energy, and that potential energy is called electrostatic potential energy. Electrostatic potential energy, say represent U, and that is equal to minus, okay, the charge, one particle, suppose the electron is a minus, proton with a plus, so there is a minus q1 q2 by 4 pi epsilon naught r. So here the E square, so q means suppose the E charge, E into E square, 4 pi epsilon naught r we get from second chapter, okay, electrostat or potential. This is the potential energy U, and what is the final energy? Means total energy, that is equal to kinetic energy plus potential energy. So that's the kinetic energy, that is equal to get E square by 8 pi epsilon naught r square, and potential energy minus E square by 4 pi epsilon naught r. If I LCM these two, 8 pi epsilon naught r square, we get E square minus twice E square, we get final expression minus E square by 8 pi epsilon naught r square. That's the total energy. And if I say that E, we get final expression of E. That's the very important here. Okay, this E energy, that is equal to E minus E square by 8 pi epsilon naught, and here we get a minus sign here, and the very significance, important significance for minus sign. Okay, so this minus sign actually signifying that or implies that electron are bound in that orbit. Because the minus sign means there is an attractive force. It's a plus, plus with a plus, that's a minus. So there is an attractive force, and that force towards the center seeking force, because force is a vector quantity. So if the vector quantity, there is a direction, and the direction is towards the center. The direction is towards the center. Okay. So that's why minus sign significance. Electron are bound in orbit. Okay. And so there is an attractive force. Clear concept. Means if say that is a plus, so means the repulsive forces means not bounded, so plus means not bounded. Actually the concept is there's a bounded. Okay, so here we find the total energy of an electrons, okay, orbital energy actually, and here the radius of the orbit. And here we jump to the next concept, is called atomic spectrum. What is the atomic spectrum or atomic spectra? Same as the concept is that. So what is atomic spectra? So each element have a characteristic spectrum. Okay, each element. Okay, all element in periodic table have characteristic spectrum. Spectra. All element have a characteristic spectra. Okay, so the spectrum of radiation. These are called as spectrum of radiation. Actually, know that dual nature. So that is wave nature and particle nature. So that's why the spectrum radiation here. When the atomic gas vapor, the concept is that when the atomic gas vapor is excited at very low pressure, usually actually when a current passing through that, so atomic gas vapor excited in low pressure. Okay, so radiation spectrum have a certain specific wavelength. If I say that is spectra means something wave, so that means a wavelength here, and it consists of the bright line on dark background. Okay, and this is suppose we next to study the hydrogen spectrum. Okay, so when atomic gas vapor, suppose note down, when atomic gas vapor is excited at low pressure, usually current passing through it current passing through it. Okay, so radiation spectrum have radiation spectrum have certain specific wavelength. Specific wavelength. Okay, that's very important. Even there is a wave, so obviously there is some wavelength. Okay, and consist of bright line. This wavelength consists of bright line on dark background. Bright line on dark background. Okay, so here we study some hydrogen spectra. Study hydrogen spectra. So suppose these are wavelength in that direction, and we choose uh, suppose first these are the spectra composed here, and these are wavelength. Okay, that lambda in that direction, increasing order. Suppose these wavelength have suppose 91 nanometer to here the maximum is 122 nanometer, and this series, okay, the spectral series is known as Lyman series. Series. Okay, and the next spectral series, suppose we choose another color, suppose here, and suppose this is, and the wavelength is starting from 365 nanometer to up to 656 nanometer, and these series have another name. Okay, and this series is called Balmer series. Balmer series. Okay, actually the Balmer formula actually find that series. So actually the Balmer formula are out of the syllabus. So here's the basic idea about the what is the hydrogen spectrum look like. Okay, derivation is very important here. So the Pasteur series is starting from suppose this one, and suppose is 820 nanometer, and suppose here and up to 1875 nanometer order, and this is called a Pasteur series. Pasteur series. Okay, so these are the hydrogen spectra. Okay, so emission line, also called, say, that is the emission line of spectrum. Okay, and when a white light passes through the gas, if a white light passes through the gas, we analyze is transmitted through a spectrometer. Actually see that the device name is spectrometer. We get some spectrum is called the absorption spectrum of material gas. So now we note that what is the absorption spectrum. Important, what is absorption spectrum? When white light passes through a gas, okay, so we analyze the transmission. Okay, mainly analysis transmission or transmitted. Okay, transmitted through a spectrometer, uh, transmitted through a spectrometer, through a spectrometer. Okay, a device. Okay, and we get some spectrum, okay, and this is called absorption spectrum of material gas. Okay, so that's the end of today's class. Okay, next class we discuss a Bohr concept. Okay, Bohr model. So Bohr model and Bohr energy, Bohr postulate. Okay, so from discussing next class, here just basic idea about hydrogen spectra, And here the atomic spectra. What is the atomic spectra? And this is a spectral line. And Balmer series is a and Balmer formula actually out of the syllabus. That's why we do not discuss here. Actually, when you discuss this, and we get actually perfectly concept about that. What is the series? What is that series, or the wavelength of the series? But there is some basic idea about what is the emission line of spectra. Okay, atomic spectra. What is the atomic spectra? Consists of bright line on dark background. Okay, when an atomic gas vapor excited to a low pressure, usually current passing through that. Radiation means there is a wave, so that means a wavelength here. Okay, and here we study the energy of a orbit, and there is a radius of the orbit, and here we calculate the force, centripetal force, and electrostatic force. Combine these two, we get some orbit and energy. And we finally first we study the alpha particle trajectory. There is some path, and there is an important factor is called impact parameter. This impact parameter actually define the deflection. Okay, we say here we see that one particle, say that one out of suppose is 10,000 or 9,000 particle, we get one particle pi deflected by 180 degree, because that's the positive particle are in nucleus, so alpha will also be the nuclear positive particle alpha charge. Okay, positive particle, positive particle, so these are like charges, so there is a ripple. Okay, so here with from alpha particle trajectory we find that upper limit, actually the approximation idea about upper limit and lower limit of nucleus. Okay, so that's the today's class. If you have any doubt, please ask in comment section. I will try to give the answer. Okay, so meet in next class. Thank you.